All right, this is a really short discussion about the differences between vector and raster file structures. And that's just to get you psyched up. All right, we can represent geographic features with either type of data model. Raster data models can represent discrete features. You don't have to use vector data. But be aware, linear features are going to be mapped as a series of connected cells. And connected, you can even have rules of whether it's just corner to corner or if they have to be adjacent. Point features are going to be represented by a single cell. And then obviously area features are a group of connected cells. So what's important about that? We're going from a polyline that has zero width, but a connection rule between two discrete points. This might be mapping the Mississippi River. So, we've got a river that might be a mile wide in some places being represented by a line with zero width. When you map a river or a road with raster data, with a matrix of cells, the cell size comes into play. So let's say this is a 30-meter raster of the United States. So now all of a sudden you're mapping a road as 30 meters wide. And that's going to be the same if you're mapping something like streamlines. If you're working with a 10-meter DEM and you're looking at a stream network, your stream might be 1 meter across, but you're mapping it as something that's 10 meters across. So just be aware. Same goes for your points. Points don't have any dimensionality to them. They're a specific XY location. When you map the same thing in raster format, all of a sudden it's become an area, and it might be 30 by 30 meters, or 10 by 10 meters, or 2 by 2 meters. Make sure that you're disconnecting the spatial model from the feature that's actually being represented. And then I think, with areas, you have to be careful in both situations to think about what does the definition of that boundary really mean. You're going to always be stuck with this kind of gridded format when you're in rasters, and if you're dealing with a 90-meter, 1 kilometer, 5 kilometer cell, this is a very artificial way to define that boundary. But so is this. You're saying that definitively we have one value here, and then right across this dimensionless line, we have a different value right here. So just something to be aware of. All right, vectors versus rasters. These are generalizations, so be careful. Typically, we use rasters to model surfaces, landscapes, slope, air pressure, solar radiation, mapping things that sort of exist everywhere across a surface or landscape, whereas vectors are better for defining specific objects, features, or locations. You can build surfaces with vectors. They're called triangulated irregular networks, and basically you have interpolated faceted surfaces, triangle-shaped surfaces connecting known elevations. The bummer about those is that they're really computationally difficult to manipulate, but they do sometimes represent surfaces more accurately than rasters. They're just really hard to work with. Rasters, on the other hand, can represent objects, and we just talked about some of the limitations of that. Very efficient storage for vector data. It's basically just a flat database file. Rasters can become rather large once they're drawn in a GIS. It's possible to compress the files, but as computers get bigger and bigger and better, well, this in one way becomes less of an issue, but on the other hand, we start modeling larger areas with more precise data, and it just ends up becoming a kind of a 50-50 trade-off. Vectors, slow processing when you're trying to move or manipulate or do geometric calculations on things, whereas rasters are built in a matrix format that's very cooperative with the way computers work. The processing on a surface or matrix is very fast. Vectors are precise at all scales because it's a distinct XY location, joined by rules, but sometimes that introduces false precision, right? Like when you're representing an entire city with a point. This is sort of a truth, but take it with a grain of salt. The precision with rasters depends on the cell size. That's called resolution. The size of the pixel determines all precision for rasters. And you have to think about what kind of features you're trying to map on the landscape and whether they'll even show up if you're working with a cell that's too big to even pick up smaller features on the landscape. Okay, so vector file structures. Basically, it's a spreadsheet. You can have a collection of points with attributes, and your attribute table is going to have a point number, an easting, northing, or an XY coordinate pair, maybe an elevation, and some kind of description or attribute stored with it. These come in formats like text files, ASCII text files, tab or comma delimited files like CSV files, Excel files, or the proprietary Esri shapefile. Wow. Here's how that can look. You can just have an irregularly distributed set of point data. Just the data exists where it is. It's not dependent on any kind of grid or matrix. Raster data, on the other hand, this is looking at a raster grid data set in ASCII file. The grid is predefined, kind of uniform cell size, and in an ASCII format, you've got header information that gives you everything you need to know about the data set. So for example, this data set has this number of columns and this number of rows. So we're going to sweep through this matrix of cell values, and we're going to go over 2,232 values, and then the next value in this sequence will define row number 2. We've got a coordinate values for the X. It's the lower left corner of this matrix, and this is the Y value that defines the lower left corner of this matrix. And from this one location, all other locations can be determined. We've got a cell size of 5. The units of measure on this are connected to the coordinate system that these belong to. That would have to be in a metadata file. And then we're using -9999 to indicate cells that don't have data associated with them, but they still have to have some indication to hold that matrix in shape. So this data set actually plots up like this. This is a Hillshade version of the elevation data set, but you can see, well, you can't totally see. You have to just imagine, if I could move this over, that you'd have several columns of no data, and then we'd hit, more than halfway across, we'd hit a cell that contains an elevation value. And then when we get to the end, we wrap down to the second row. And it's a matrix built like that. It's very clean and very efficient for computing. Okay, raster cell size units. The resolution is the size of a cell, it's the length of a cell, and the units for resolution come from the coordinate system. It can be in degrees, which would be a geographic coordinate system, like latitude and longitude, or it could be in meters and feet. These are planar Cartesian units of measure. When you're working with rasters, it's really important to work with a projected coordinate system. You want your rasters to be projected. ArcGIS Pro is making it easier and easier for us to work geodesically. But because distances and areas are fundamental to raster analysis, and because rasters are built of squares that have, or cells or pixels that have area, it's really important to work in a projection. You don't want to have units of degrees when you're dealing with rasters. So as easy as ArcPro is making it for us to work in geographic coordinate systems and make area and distance measurements geodesically, project your rasters. All right, here's a plot showing your ability to care increasing as I give you some information, but then we reach this point right here where you kind of stop caring the more information I add. And this is critical mass, and I'm wondering if that's where you are right now. Any questions, let me know.